In this video, I'm going to show my calculations for the sniper scene in Call of Duty Modern Warfare. In that scene, they're in the top of a large, looks like abandoned building or parking garage or something. And there's a bad guy a long ways away. And so the guy that's helping the sniper tells him that he needs to consider the Coriolis effect. So what I'm going to do here is show what I figured out with the Coriolis effect and how I would calculate that for that particular situation in Pripyat, Ukraine. This is another rabbit hole of a lot of complicated models and one calculation leading to another, which leads to another. So there's a lot of chances to make errors here. I could make an error either with my model, because I have to come up with these models to get my calculations from them, or else I could make errors with my calculations. And every time I calculate something, I have to use that answer to plug into a different equation, and then use that answer to plug into a different equation, and it goes on and on for many, many equations. So there's a lot of potential to make errors when I do these kind of videos. But if you are like me, where I never really knew much about the Coriolis effect and didn't think much about it, I just thought it would be something that would be too complicated to figure out for my math level. Then stay tuned and you can see what I figured out. It looks like it's just some simple SOHCAHTOA trigonometry, introductory trig. So you can see my video on the intro trig if you want to be able to follow along with what I'm doing. And you can see what I figured out here. But it all looks like it's pretty logical and pretty reasonable when I go through it. So yeah, granted I made everything up here, or I just figured all this out on my own, which does lead to the potential for a lot of errors, but the logic seems straightforward. Okay, so in the video game, Sergeant Macmillan, I believe his name was, they're up in Pripyat, that's how you pronounce it, Ukraine. It's about 51.4 degrees north. My Google, Google Earth app lists it as 51 degrees, 24 minutes north. This is right outside the city, so it's kind of an estimate. I take those 24 minutes, and that's 24 minutes out of 60 minutes. 24 divided by 60 equals 0.4. Therefore, this is 51.4 degrees north, and that is the latitude. And it's 30.03 degrees east, but I don't use the longitude. So here, if we're looking at the Earth, at the equator right here at 0 degrees, we go up to 51.4 degrees north, where Pripyat, Ukraine is. And basically all we want to do is look at the cosine of this angle, and that will tell us the effective disk, or the size of the disk that these people are spinning on. The equator has the largest velocity because the Earth spins oriented to the equator. So as you move up here, it's kind of like moving in toward the center of a merry-go-round. As your radius gets smaller and smaller, you spin at a lower and lower velocity. I checked Google to see if there was any information on how far that shot was in that video game. Google AI said it was somewhere around 1,000 meters or so. I don't remember exactly, so that's what I'm using. And if you're at 51.4 degrees north and you're shooting 1,000 meters away, say directly to the north, then the target will be at 51.40899 degrees. These angles are not to scale. I just exaggerated the angles for visual purposes. But as you can see here, where the person is shooting from this latitude, if they're shooting up to the north, this person will be spinning faster than their target will. So that means they need to lag the target or aim to the west, because it's like these people are on a fast-moving train and they're shooting at a slower-moving train. So what I do is get the velocity of each location and find out what that velocity difference is. Likewise, the the shooter could be located at the higher latitude and shooting down to the lower latitude. And in that case, they will need to lead the target because that part of the Earth is spinning faster than they are. And when they lead the target, that means they'll need to aim to the east if they are shooting directly south. So they're shooting south or they're aiming south, but they'll need to lead the target to the east. So first I need to find the velocities of these particular disks that these people are spinning on. I just pretend the Earth is cut up into a bunch of disks, and the smaller the disk is, then the slower that person is spinning. Take coast 51.4 degrees equals adjacent over height. The height will be the just the mean radius of the Earth, 6,371,000 meters approximately. Feel free to plug in more accurate numbers. I'm just doing this to show the calculations and to get a gist of the situation. This will give us the radius of our disk right there. That's what adjacent equals. Multiply by 2 pi and we get the circ. The Earth spins around every 24 hours. So that means it completes one circumference every 24 hours. So we take that circumference and divide by 24 hours and divide by 60 squared. That's 60 seconds per minute, 60 minutes per hour. And then this will give us our velocity in meters per second. And this will be 289.0510 meters per second is how fast this disk is spinning, or how fast that train is moving, if you want to use the train analogy. On the next page, I'm going to show how I got this latitude right here, and I'm going to calculate the velocity of the spin at that particular latitude. All right, here's our circle. Theta over 360 equals the arc over the circumference. If theta, which is the angle, was 90 degrees, 90 would be 1/4 of 360. Therefore, the arc of that angle would be 1/4 of the circumference. So theta over 360 equals arc over circ. This is the same thing as the distance over 2 pi r, and that's the distance that he is shooting. He is shooting 1,000 meters, so theta over 360 equals 1,000 over 2 pi r. 1,000 meters is the length of our arc right there. Then theta equals 0.00899 degrees. We add that to the 51.4 degrees north, and we get 51.40899 degrees. And that's what I have right there for the location of the target. Right here I added the two latitudes, but if I wanted to, I could subtract the smaller latitude from the larger latitude if I was aiming south. And if that were the case, then I would need to calculate the velocity of that particular disk on that section of the Earth at that point. Now I have my angle. Now I need to calculate the velocity that that particular disk is spinning. I almost forgot to mention, if you see the video game, you can actually watch clips of it on YouTube. The wind is blowing all over the place, so that flag is just fluttering in all different directions. So on the wind part, you're just on your own. You just have to watch the flag in the video game to get an idea where you're going to shoot or where you're going to aim. But this part here is just for the Coriolis effect. Okay, so let's do the same math for cos of 51.40899 degrees. That gives us the adjacent, which is the radius of that disk. Multiply by 2 pi to get the circ. Divide by the number of seconds in a day, because the Earth spins around that circumference every 24 hours, which is that many seconds. We get 288.994 meters per second. So that is how fast the person is spinning at that particular latitude. What's the velocity of that effective disk on which he or she is standing? Let's take the difference between our two velocities to find out what the relative velocity is. In other words, how fast is the larger disk spinning compared to the smaller disk? That comes out to be 5.7 centimeters per second. That was a sloppy centimeter. Now we know the velocity difference, so let's find out for how long that bullet will be in the air. I'm going to say he's shooting at 1,000 meters. I don't remember what it actually was in the video game. I think that's about 0.6 miles, so that's pretty far. And I'm going to say the average velocity of that bullet is Mach 1, which is about 343 meters per second. Meter divided by meter cancels. That means the bullet is in the air for about 3 seconds. I made these numbers up, by the way, so feel free to plug in whatever numbers you want to make this more accurate. But what I'm going for here is just a general gist of the situation, or a general understanding of the situation, and I figure these numbers will put us in the ballpark. And here, just remember, we don't want the muzzle velocity. We actually want the average velocity of that bullet, because that will tell us for how long that bullet is in the air. So let's say the bullet's in the air for 3 seconds, which might be a little longer than normal. But let's say he's taking a longer shot with a smaller caliber rifle. I don't think he was in the video game. I think in the video game he might have been using a 50 cal. I don't remember. It's been a long time since I played it. So 3 seconds is for how long that bullet's in the air. 1 second per 5.7 centimeters. because that's the velocity difference between the two discs. That comes out to be 17.1 centimeters, or about 6.7 inches. That means if he's at this point right here at 51.4 degrees north and he's aiming directly north, he'll need to aim about 17 centimeters. Sorry, I wrote here, he'll need to lag the target, which means he'll need to aim about 17 centimeters or about 7 inches to the west of the target. And that's because you could think of both trains here traveling east. He's on the faster train and he's shooting at a slower train. And then likewise here, if the person is up here at the northern location and he's shooting directly south, he'll need to lead the target because this person will be on the slower train and he'll be shooting at a faster train. So he'll need to lead the target by aiming 17 centimeters or about 7 inches to the east. A lot of times on these projects here, when I go down these rabbit holes, and I have to come up with my own models, which could be wrong, and I have to go through a ton of calculations, and I can make a mistake on any of those. I am taking a risk of getting some stuff wrong. But like I said earlier, I think this really sort of makes sense. I mean, you're either on the fast-moving disc or the slow-moving disc. You simply take the cosine to evaluate the size of your disc and how fast you're spinning. So if this is not exactly how it's done, I would imagine it's pretty close, just logically.